Hi, my name is Emily Jong. I'm a graduate student from Caltech, and I'm going to be telling you about one aspect of my work that handles small microscale collisions between droplets in the atmosphere. Let's start with a little bit of background. As we all know, humans exert an influence on the climate, for instance, by pumping carbon dioxide and other greenhouse gases out there, which we know have a warming influence on the planet on the order of 2 watts per meter squared for carbon dioxide, for instance, with relatively low uncertainty bars. At the same time as we pump greenhouse gases, we're also adding aerosols to the atmosphere. Things like soot coming out of your tailpipe. These aerosols have mostly a cooling effect on the atmosphere to our understanding. Aerosols themselves reflect incoming sunlight, and aerosols serve as the nucleation sites to form clouds. And if you've ever been outside on a cloudy day, you'll probably be familiar with the idea that clouds tend to have a cooling effect on the climate. However, you notice that both of these cooling effects, and especially the aerosol cloud interaction cooling effect, has an uncertainty bar which is a much larger magnitude even than our understanding of the effect itself. And it's because these interactions happen at the very small micro scale. So, what are these microphysics that I'm talking about? Well, microphysics refers to two things. The first is all of the liquid and solid particles suspended in the atmosphere. All of these aerosols that I described to you, all of the liquid cloud droplets or ice crystals that make up clouds. It also refers to all of the processes that govern how these particles interact with each other and with their surrounding environment. And these processes are numerous and complex, everything from condensational growth of cloud droplets onto an aerosol and coalescence of these cloud droplets, which I'll describe shortly, to the many more processes that can happen higher up in a cloud once we begin to reach freezing temperatures and incur mixed phase microphysics. As a result of this complexity, all of which is happening at the micron size scale, these microphysics are a dominant source of uncertainty in our understanding of changes in the climate system, simply because it's impossible to model all of this complexity at such a small scale in a large-scale weather or climate model. So let's be a little bit more specific about what these models look like. When we talk about modeling clouds in the atmosphere, we're talking about a climate or weather model which divides the atmosphere up into grid boxes in the horizontal and in the vertical. In a typical climate model, these grid boxes might span tens or hundreds of kilometers each, much larger than the scale of a single cloud, much less than the scale of all of these cloud droplets within the cloud. Instead, we keep track of grid mean quantities, conserved quantities like mass, momentum, energy, and the amount of water in its various phases. The other processes which we under-resolve include things like radiation, turbulence, and of course, microphysics. These processes like condensation and evaporation, precipitation, phase changes between different states of water, and more. All of these processes have to be parametrized or approximated because we cannot resolve them directly. And as if that weren't hard enough, these processes also exert influences on each other. For instance, the albedo or reflectiveness of a cloud has a feedback on radiative energy processes. And for instance, release of latent heat during evaporation or condensation also has an influence on the momentum budget and turbulence. Let's get a little bit more specific about one process that I'm focusing on in particular. Cloud droplets are all falling relative to the air around them. That air is, of course, moving upwards, which is why clouds appear stationary in the vertical. These droplets are falling at different speeds, with larger droplets tending to fall faster than smaller droplets. And because of that, droplets often come into contact with one another. If they're not moving too fast relative to one another, they will coalesce or merge to form a larger droplet. That process is exponentially getting faster and faster as these droplets collide and coalesce and grow larger, until the droplet is large enough that it actually falls out of the cloud. Its terminal velocity is faster than the updraft. So this process of coalescence or collisional growth is the key to why precipitation happens, at least among liquid phase droplets. What do we need to know about the hydrometeors within our grid box in order to accurately predict this rate of coalescence or precipitation? Well, at its root, we need to know how many droplets are there and how large are they. We typically represent this as something like a particle size distribution, where on the x-axis I'm showing the radius of particles, and on the y-axis I'm showing the mass density of particles that exist at each of these different sizes. We can also describe the coalescence rate through something that's a bit more fundamental, a collision rate, which would describe the rate or probability of collisions between a particle of size x and a particle of size y. This gets plugged into some spooky looking equation like the Smolowski equation or the stochastic collection equation, which effectively gives us a population balance describing how the population of droplets evolves in time according to their various sizes. A typical climate model doesn't go through this level of complexity. We use something called the classic method of moments, where we keep track of integrals of the size distribution rather than the size distribution of itself. And typically, we'll split this size distribution into two categories. One category we call cloud, which refers to small droplets, and one category we call rain, which refers to larger droplets. When we need to know more detail about the size distribution, we relate these moments back to an assumed underlying closure form, something like an exponential or a gamma distribution, and we invert the parameters of that distribution given the instantaneous rate of moments. From there, we can evolve these moments in time through approximated equations based on these closure assumptions. The problem becomes how we move mass between these different categories, because cloud and rain are inherently just two different regimes of liquid droplets, all of which are undergoing the same sets of processes. So for instance, how do we decide how quickly the number concentration or mass concentration of cloud is being converted into mass of rain? Typically, climate models today do this with a conversion rate, some sort of empirical parameterization that might have some basis in theory. But the problem here is that we began with artificial categories, cloud and rain, leading to the need for this artificial conversion rate. And more fundamentally, we're limited in terms of the accuracy or complexity that we can represent by making this fundamental assumption of two categories of hydrometeors. We'd like to do better. We'd like to approximate the size distribution itself in a way that's computationally tractable for a climate model. Again, asking this question of how many droplets are there and how large are they? If we think of one traditional type of approximation, we could think of this as a histogram or a bin type approach, where we divide the particle size range up into discrete bins and keep track of the number or mass density associated with each bin. This is a technique called the bin method or flux method, and it's been around for some time. But we require on the order of 64 bins to accurately represent a particle size distribution, making this method too computationally expensive for use in any sort of large-scale modeling. So let's see if we can do a little bit better. Let's come up with an approximation instead, which is itself a sum of many sub-distributions which look like particle size distributions themselves. In particular, we're using something called collocated basis functions, where each of these sub-distributions is a basis function that is centered at a particular size xk and has some other hyperparameters. We then, in a similar spirit to the bin method, evolve the number density associated with each of these basis functions forward in time, but now using this smooth representation. So let's see how well we can do at representing, say, an initial distribution, which is fairly narrow and centered at small droplets, and seeing how that distribution evolves as the droplets collide and coalesce to become a slightly broader distribution centered at larger droplets. Well, we can compare a few different methods against a high-fidelity reference case where we represent individual droplets, 2 to the power of 16 of them to be precise. Again, not a real solution here, just a reference case. We can compare it against, for instance, the old method, the method of moments that I described to you earlier, which is plotted in red and uses 3 degrees of freedom, and also against one version of this bin or spectral method that uses 32 degrees of freedom. And you'll see here 2 lines using this collocated basis function approach. And what we find is that by using 16 degrees of freedom in this approach, we achieve comparable results to the bin method. We see a similar accuracy complexity trade-off if we look at a variety of initial conditions, as well as a variety of different potential coalescence dynamics or rates. The fact of the matter is, we're using half the degrees of freedom as a traditional bin method to achieve the same level of accuracy. Therefore, we're cutting the number of tracers we need in the system by half, and we're actually cutting the number of operations that we need to perform by 25%. But can we do better? In this collocated basis function approach, we're inherently being inflexible. We're only allowing one parameter of each subdistribution to vary, that being the number density. What if instead we return to this idea of a method of moments so that we can allow all the hyperparameters of each subdistribution to change? Not only its number density, but perhaps its mean mass or its shape factor or sigma, for instance. That's exactly what we came up with in a new flexible method of moments. Let's go back to this idea of representing our particle size distribution as a sum of subdistributions, where we have some coalescence rate that describes the rate of collisions between particles of size x and y. If we take a polynomial approximation of that coalescence rate and exploit the structure of that Smolowski equation integrals, we can do some pretty clever math. For instance, if we take a smaller particle from a smaller subdistribution and a larger particle from a larger subdistribution and coalesce them, we can always place that mass back into the larger subdistribution. And when we collide 2 particles from the largest subdistribution, there's nowhere else to place that mass but back into the same subdistribution. Of course, the problem comes in when we talk about colliding two particles from the same subdistribution, in which case we might want to put some of that mass back into the same subdistribution and some of the mass into the next largest one. In this case, we apply a mixing rule, or a weight function, which can be applied across the entire domain of particle sizes and isn't specific to the number or type of subdistributions we're using. This could look like something like a Heaviside function, where we're effectively limiting the mass range for each subdistribution, or even something more complex. How does this work in practice? Let me show you an example. We're going to begin with a small and narrow peaked distribution, where all of the mass is concentrated in the smallest subdistribution of the four that we're using. After some time, particles collide and coalesce, and that mass begins to get transferred into the next two largest subdistributions, which you see in the top middle plot here. You'll also see that all three parameters of the second subdistribution, the one in orange, have changed over time. In the top right-hand plot, we see that the number concentration in blue has increased and then decreased, and that the average mass of this subdistribution has steadily increased. By the end of the simulation, we've transferred most of the mass to the two largest subdistributions. So this gives you a demonstration of how this would work within a box, but let's look at a more complicated and semi-realistic cloud. If we look at the particle size distribution and compare it against a higher complexity, high fidelity particle-based method, we can also confirm that if we use more modes or more subdistributions to represent our results, we obtain higher accuracy results. For instance, in the end here, we're better able to capture the bimodal nature and the broad spreading of the particle size distribution. Now let's look at our one-dimensional cloud. We're going to start by initializing a lot of small droplets at around 1.5 to 2.5 kilometers altitude, which is plotted on the y-axis. On the x-axis, I'm showing you the quantity of small droplets, which we're calling cloud, just for the sake of efficacy, and large droplets, which we're calling rain. These droplets are going to be colliding with each other, coalescing and growing larger, and also falling with respect to time. So if we start to allow that process to initiate, we see that our method initially produces rain, as we expect to see. And those rain and cloud droplets are also starting to sediment according to their relative velocities. As the simulation continues to proceed, most of the cloud has been depleted and turned into larger precipitation range droplets, which are falling faster and faster, until eventually the cloud and precipitation starts to touch the ground and rain out all of the moisture that was initially present in the system. So this has been a source of validation, but let's go back and look at the big picture of how this new type of method compares with a standard approach. In a traditional method of moments, we might make a choice, for instance, to use two moments to represent our system, a cloud category and a rain category, and a mass distribution associated with each of those. We then have some sort of parameterization that describes the rate of change of cloud into rain, for instance, a Kessler type in this case. And we can look at our results, for instance, describing the quantity of rain or large-sized droplets that are present at various altitudes and various times in the simulation. Let's say we want to do better, though. We want to get a little bit more accurate, and so we choose to use 4 moments instead. We add the number concentration to each of these two categories, and we have to choose a new and different parameterization that can take these 4 moments as input. But as you see, our results are completely different. These methods are not necessarily self-consistent with one another. As you increase the complexity, you're not guaranteed to converge toward consistent results because of these conversion rates. In our flexible method of moments, however, we have the opposite case of self-consistency. We can begin with the case of 4 moments, for instance, 2 subdistributions, again, looking at at what altitude and at what time rain begins to form. Let's say we want to up the ante a little bit and use 7 moments instead, maybe 3 subdistributions, 2 exponential and 1 gamma. We notice that the rain initiation time is a little bit earlier, and rain forms at a slightly higher altitude. And eventually, this method, in fact, converges to a particle-based method, where we see rain present almost everywhere in the system. This shows that this new method is not only self-consistent, but also converges towards higher complexity methods. So to summarize, I've shown you a new way to model particle size distributions with a focus on the coalescence process that leads to precipitation. I first showed you a smooth collocated basis function approach to representing a particle size distribution, which can outperform traditional spectral methods. I then showed you a way to generalize the method of moments in order to use the fundamental rate of collisional coalescence rather than conversion rates, so that we can achieve a flexible, self-consistent, and convergent method. We're currently working on validating this method in a 3-dimensional atmospheric simulation with the goal of ultimately implementing it in the Klima Earth system model. If you have any questions, please feel free to reach out to me on my email. Thank you.